If you are thinking linear versus exponential. Exponential, actually, the graph looks something like this. I'll come back to it. Where linear, it's a straight line. So take this bowl, and it sounds disgusting now. Let's assume we have a bug in this bowl. One bug. And every minute, that number of bugs will double. So right now, we get this jar or this water bowl. Inside that, there is one fly. We'll use a fly. A minute later, we're going to have two flies. Every minute, the number will double. The next time is going to be what? 4 flies. Then the next minute is going to be how many? 8. So every minute, that number will double. Here's the question for you. If it takes 1 hour to fill this to the top, how long would it take it to be half full? How much? 30. I got 30 minutes.
45 minutes.
No.
59 minutes.
Why 59?
Because it's half full then and then it doubles.
It doubles every minute. So it takes 59 minutes to be half. Then the next minute is going to double. When you said 30, you were thinking linear. If it takes half an hour to fill it, hour to fill, it's going to take half an hour. That's not how exponential functions work. So this will take actually 59 minutes to be half full. Because the next minute is going to double that, will double. Okay, another one. This exponential, this is fun stuff we do. There's a piece of paper in my hand. I cut it once. How many sheets do I have? 2. Cut it twice. 4 sheets, right? 3 times, 8 sheets. 4 times, 16. So, 1 cut, how many sheets we had? 2. 2 cuts, the second cut we have how many? 4 sheets, right? Because you doubled that number. 3 cuts, you're going to have what? 8. 4 cuts, you saw me do that, you have what? 16. If I do it 50 cuts, I'm not asking how many sheets. The question is, and you stack these pieces of paper, how high would they go? How much very high? Would it be like the size of this table? Is he asleep? Wake up! Come on! Since 4. So, you listening? How high is it going to go? What do you think? Is it like a 1 foot? 2 feet? Okay, more than that, a mile? I give you a no. Well, wait, let's give you a thickness of a paper. Because you can't really answer without the thickness. Let's say this construction paper, 1 millimeter thick. It's a little bit thicker than normal paper. Because that makes the math easy, 1 millimeter. How many miles would it go? How many miles? I already gave you a hint. Well, okay.
50 millimeters?
The thickness?
Yeah.
1 millimeter.
Yeah, but wouldn't the whole thing be 50 millimeters?
Oh, no. Oh, no. You know what 50 millimeters is? 50 millimeters is 5 centimeters. You tell me it's going to be like as thick as a phone book. Well, it could be. But I just made a mistake by telling you how many miles high. I never seen a phone book that's a mile high, a mile thick there. Or even how many million miles high. Millions.
Maybe to the moon?
I think probably farther than the moon. Way farther. Well, let's think about it. I don't even this calculator can do that high. Let me get a bigger calculator. 1 cut is 2. How'd you get 2? 2 to the power of 1, which is 2. 2 cuts, it's 2 to the power of 2, which is what? 4. 3 cuts, 2 to the power of 3, which is what? 8. 4 cuts, 2 to the 4, which is what? 16. If I do 50 cuts, how many sheets of paper I'm going to have? Ready for that number? 2 to the power of 50. Hope you have a big calculator there. It's 1.12589 times 10 to the power of 15. I stopped writing after a while. That means move the decimal point how many places to the right? 15 times. That's how many sheets of paper? Each one in millimeter. Well, let's go back. I know I'm a little bit decent with the metric system. This is a ruler. I don't know if you can see the dashes on it. Each one of these is a millimeter. If you divide it by 10 is what? Centimeter. A meter, which is a little bit more than a yard, is actually 1,000 millimeter. So let's take that number and divide it by 1,000. Because that's in millimeters right now. By 1,000. That will tell me how many meters that thing is. So it's going to be 1.12589 times 10 to the 12 meters. If you know the metric system, how many meters in a kilometers? 1,000, right? So divided by 1,000. Ready for that number? It's that many kilometers. High. Do you know how big the kilometer is? 0.62 miles. If you're a runner, when you run a 5K race, that's what? 3.2 miles. A 10K is 5.2 miles. So 6.2 multiplied by 0.62. And here's how many miles high will go. See that number? 698,057,942 miles high. Almost 700 million miles high. 50 cuts. So when you said the moon, not even close.
It's more than double the distance to the moon.
Is it?
Yeah, just looked it up.
Yep.
It's 238 million. Yeah. There's 1,000.
That can be million to the moon.
1,000.
1,000, yeah.
Way higher.
Yep. I'll give you one more example before we start doing some math, because I just want to show people, because it doesn't seem high, like when you look at these, like, really? If I cut them another, we did 4 cuts. If I do another 46 cuts, I'm going to go that much? Oh, yeah. Couple more cuts, it becomes a phone book. You flip that phone book, it's 2 of them. 2 of them become cinder block. It's probably 4 phone books. Then 2 more cinder blocks. Then it's a yard. Then it's 2 yards. Then 4 yards, and start to add up quickly. A good example to see that, I'll give you this, money, because everyone likes money. Here's what we know about money. If you can get 10% interest on your investment, your money will double the rule of thumb. Anyone knows the rule of thumb?
7 years.
7 years. Actually 6.93 years, but we'll do 7 years. Watch this. Let's see, when you were born, Grandma decided, I like Ricardo. She was lying, actually, but she goes, Ricardo, I'm going to leave you $5,000 here. When he was born. And she went somewhere and she managed to get 10% of the stock market, put them there, had investor friends, put them in the market. The market is really, you'll be fine. After 7 years, let's see what's going to happen to that money. At age 7, Ricardo will have what? 10,000, double that number. Double that. Doubles every 7 years. At age 14, Ricardo, you're going to have what? 20,000. At age 7 more, 21, you'll have what? 40,000. We know if we told Ricardo that's 40,000 for you, he'll take the money, buy a sports car with it, and he's done. But we never told him. At age 28, double that number, 80,000. At age 35, you have what? 160,000. Start to look better now. At age 42, 320,000. We're going to make you a millionaire, Ricardo. At age 49, you have what? 640,000. At age 50, what is it? 56, you have 1,280,000. And you had a plan to retire around 62, you know? At age 63, 2,560,000. So you were thinking of retiring at age 63, but you say, I can't afford to retire, because you had no idea about that money there. I can't retire. I can't afford to retire. I need to work. So you work, you're 70 years old now. And you have what? 5,120,000. Now notice your age now is over 70. Guess what happens when you hit 69 and a half? You get a letter from the government. You got to start taking money out of your money that you have there. Why? Because they want the taxes on it. At 69 and a half, you must take some of that money out. You don't have a choice. You can't say, I don't want to. So you get, Ricardo gives that letter, goes, what money? I don't have anything. So Ricardo goes to the bank, says, I'd like to close my account. I guess I have an account with you. And I'd like them cash. Cash? Do you know how much you have? No. 5,120,000. It took 70 years to build that money. But watch this. What about if Ricardo were to plan for retirement? Because you know what? I wasn't even counting on them. I don't even need it. I have my own retirement. 7 more years, just like that fly there. In 7 more years, it took 70 years to make, 5 million? Now it's going to take 7 years to make another 5 million. So at age 77, he has 10,240,000. 77 years to get to 10 million. 7 years later, 84, 10 more millions. 20,480,000. Guaranteed now that the water that Ricardo's drinking has some probably antifreeze in it. Because the kids want him dead and they want that money. Like, get the hell out, Dad. You've been out here for a long time. But that's what exponential is. It's not just linear. It doesn't just go a straight line that some of you thinking, it took me 7 years to make that much money. It's going to take that 70 years to make the same amount. It doesn't. It goes like this, start to rise really fast. But it doubles every 7. When you put small amount, the saying, the rich gets richer. Why? Because you and I, we go to the bank, you put 5,000. That's good. Bill Gates goes and puts 10 million for his kids. Do that math for 10 million, starting with 10 million. What would you have? $1 billion? Or more? Trillion? The next question, where do you get 10%? I can tell you, if you put money in the stock market for the last 30 years, you average over 10% return. You probably average 12, 13%. The market's not that bad. Some days are bad, but overall, we've been doing extremely well. I can, just a mutual fund, just quickly, I'll just check one. What Fidelity did, for example, Fidelity has a fund called Contra Fund. That's really a good fund. I don't recommend, don't listen to me. I lost a lot of money in the stock market. But that's a fund. I said to myself, I should have put my money in it as a safe one. But I didn't listen to myself. I decided to play the stock market, and I lost a lot there in it. Took my kids' college funds and drained it. FCNTX. Just curious what that fund did in the past 10, 15 years. 20 years, maybe I can get it. Lifetime, if I can get it. Do we have any numbers on it? Performance. Can I get all of it? I want to get all of it, if I can get it, since that thing been existing. I have some fund in it, so I have to log into my account to see what that number. Just to give you an example, like 2011 was a minus 0.14%. 2016, that fund was 16.26%. 2013 was 34.15%. 34. 2014, 9.56. I can guarantee you that fund did more than 10% over the inception, the life of that fund, mutual fund. So there's a lot of mutual funds that can get you 10%, a lot of them. Yeah. But when the market goes down, they go down quickly with it. So do you have the stomach to go on that ride or not? And if you do, you go, let me ride this. I'm young. If you're old, you can't afford to go on it. So that's how the exponential functions work. So let's look at some of them mathematically. What is the equation for them? So the equation for exponential functions normally will look like this. Y equals b to the x. B is the base, that's why we use the letter B. X is the exponent. So if I want to graph y equals 3 to the power of x, what does the graph will look like? We can make a quick table for that. Here's x and there's y. Let's pick values for x. 0, 1, 2, 3, negative 1, negative 2, negative 3. When x is 0, what is 3 to the 0 power? 1. 3 to the 0 is 1. When x is 1, what's 3 to the 1? When x is 2, what's 3 squared? When it's 3, 3 cubed, 27. When it's negative 1, very good. When you have negative exponent, the rule says a to the negative n is what? 1 over a to the n. 1 over 3 to the first, which is 1/3. 3 to the minus 2, it's 1 over 3 squared, which is what? 1/9. 3 to the minus 3, it's 1 over 3 cubed, which is what? 1 over 27. And you'll notice that number never actually hits a 0. It gets really small, but we'll never get the 0. So if you try to graph them, you go 0, 1. That's this point. That's 0, 1. 1 and 3. 2 and 9, way up there. I'm not going to do 3 and 27. I don't have a ladder for it. Negative 1 and 1/3. Negative 2 and 1/9. Negative 3 and 1 over 27. And what do you notice about the graph? It approaches that line, never touches the x-axis. And it goes like this. And that's your 3 to the x's. If I wanted to graph 4 to the x, what do you think the graph will look like? 4 to the x. This is 0, 1, this point, by the way. What is 4 to the x? What's 4 to the 0? 1. So 4 to the x will have the same shape except sharper. It rises faster. And it falls faster. Never touches that line. 4 to the x. And if you did 2 to the x, what would it look like? 2 to the x will be flatter. And again, slower falling. But all of them go through the points 0, 1. Every one of them. Now, if my exponent is negative instead of positive, if it was 3 to the x, it was 3 to the negative x, this is, by the way, called a growth problem. As x increases, what happens to it? It rises. It gets bigger. It's a growth problem. I can tell you where we use growth problems. Banks. When you put money in the bank, the amount of money you will have is computed by using this equation. That's what all the bank uses. A0 is the initial deposit, e to the RT. Remember grandma who left us that $5,000? We said your money is going to double every what? Every 7 years. Let's put in 7 years and see if it's 10,000. Actually, it's 6.9 years. So this will be more than 10, maybe 10,100 bucks extra. Well, let's see that. If you put 5,000 here, e to the power, what was the interest rate we were using? 10%. What was the time? We said 7 years. Does that give me a 10,000? Let's see. That's 5,000 e to the power 0.1 times says 0.7. What is 5,000? E to the power, whereas that's over the natural log, where's the e? E to the power of 0.7. 10,000, $68 and what? 76 cents. We say your money will double every 7 years. Thank goodness I'm good in math. I'm decent at it. And I'll explain to you. I had a friend of mine who is actually a financial advisor comes to my house, and he knows I'm not going to listen to a single thing that he's going to offer me. But he comes in with a plan now, and he said, you know, I switched company. This company is really good, and we give you personal attention. We do this and that, and all the good stories that goes with it. We tell you what to invest your money in. First, I'm not going to listen to what he tells me to invest it, but I said, what do you charge? He goes, 1.5%. Now, it doesn't seem not that bad, 1.5%. But imagine I've done this to a senior citizen, which a friend of mine actually goes, speaks to them, asks me if I can come talking about money. Imagine you're a senior citizen and you've been saving money and you have $500,000 aside right now. Now, if you only have $500,000 and that's all you have, you're in trouble. So it might sound like a lot of money, but it's not really a lot. So you have $500,000. $500,000. That's the initial investment. And you go to my friend here, his name is Ken. Ken, I'd like to spend the money, invest the money with your company. Ken says, we charge you 1.5%, so whatever interest we make, we're only going to keep 1.5% interest. Ken is really good at what he does. Let's say he managed to get you 12%. He managed to get 12%. So let's see what will happen to you. This is what Ken's company is going to collect. Because they took that money. So the amount of money they're going to collect is the initial deposit, e to the RT. It's 500,000. E to the power, interest rate, they get 12%. And let's say they put the money, pick a number of years. Let's use a decent number. What, 20 years? For 20 years. It's doing really good for you. So what's that number? 20 times 0.2, 0.12, is that 2.4? So let's see, what's 500,000 times e to the power, we said 2.4. Good job, Ken. 551158819. $5,511,588.19. You excited? Ken, I need that money back. Ken goes, oh yeah, you want it back? We can cash it. But remember what I told you, it's 1.5% I'm going to keep? I said, yes. So you're going to get, actually, that's you. You're not going to get the 12%. You're going to get what? 10.5%. So the amount of money that you're going to get is the 500,000 e to the power 0.105, 10.5%, times the number of years, which is 20. $2.1, so 500,000 times e to the power of 2.1. 4,083,084.96. So that 1.5%, which doesn't seem that bad, what did that company get? Almost 1.5 million from your money. Most companies, let's say, will get 1%, 1.5, 1.25. That's what they charge. It doesn't seem that bad when you talk to them, but when you look, especially if that money sat for 40 years, that could have been $7, $8 million difference. Yeah. That's the growth, you know. The other side of it, do you want to handle the money yourself? If he's good at it, he's going to get you 12%. It might be worth giving that $1 million. Because if you did it, you probably get 6%. Put it in the bank and get 2% if you're lucky. And that 500,000 will be worth 520,000 20 years from now if you get 2%. But it just looks like, oh, it's only 1%. Every time I do an example like this, the senior citizen, they get really upset. I didn't know how much money they're taking. Oh, yes. That's a growth problem. A decay problem, and I'll do that. We're still in the first section. A decay is actually where the exponent is negative. So if you were to graph that, guess what the graph will look like? We can make the table, but the graph will be reversed. Still going to go through 0, 1. If I did 3 to the negative x, it will look like this. That's called a decay problem. Our book, at least in this section, I'm looking to see, they're not really talking about decay and growth yet. Where do we use decay problem? Nuclear waste, for example, half-life. Carbon, half-life. Can you look and see what carbon half-life for carbon is? Half-life for carbon?
Capacitors.
Well, they do have a decay problem. Yep, you're right. They discharge that way. I'm just looking for carbon because do you wonder sometimes they find a fossil out there, they go, oh, we believe this is from a human that was here 7,000 years ago.
Carbon's half-life is about 5,730 years.
5,730 years. That's the half-life of carbon. What does that mean, half-life? If we find a fossil out there, a bone here, that's a bone here. You know, we need to know, looks like an animal bone, a human bone. Oh, people were living here on Earth at that time. Imagine how much carbon in it. They can take that piece and measure how much carbon left in it. And they go, you know what? There is a 20% carbon left in it. We can estimate now how long this one actually, person, animal, been dead. And the way we do that, the equation, the same thing. A equals A0 e to the negative RT. Bless you. We need to know what the rate here of decay, what percent disappears. What half-life tells me here, every 5,730 years we have half the amount. So I can find what R. Let me find R. So if I have 1 gram of carbon today, 5,730 years from now I'll have half of that. So 0.5 equals 5,730 e to the power negative R. Oh, I'm sorry, I put it in the wrong place. If I start with what? I said, how much are you going to start with? 1, right? You'll have half of it. E to the power of 5,000. God, let me put them in the right order. It's correct, but I want to put them in the right order. We don't know what R is. We're looking for it. 5,730 years. I was about to write like this, Papa. And now I got to solve for R. How would I solve for R? Because once I know what R is, I know the equation for carbon, and I can look at the percentage and tell you how many years. I can solve it for T now. I just put 0.2 here once I know R and just go through it. Well, I can't tell you how to solve it yet because we didn't cover the topic. We'll cover it today or next class. You just got to trust me on that number. That number is R, if you do the math, again, you got to trust me on that math, 0.000121 approximately. Once I know what the rate of decay for carbon is, any piece I find, once I measure the carbon, I can tell you how old that piece. How? I go back to this equation. Where R now is what? R is negative 0.00012 T. So that piece of bone that we have has 20% carbon, 0.20 equals 1 e to the power of negative 0.00012 T. Again, you don't know how to solve this yet, but the answer to that will be how about 13,304.6 years? We said this person or this animal been dead for 305 years roughly. The question is, how did I solve this one? How did I solve for R here? That's really what the question is. You don't know that. And that's section 13.2. Is it chapter 13, right? Yep. So now we're going to look at the logarithmic functions. So I'll stop this video for this section.